Hey guys, hope you're all doing good and welcome to a new video. So most of us know how a battery works and what are the various parts in it. However, do we know how the battery gets a particular rated voltage? Well, that's what we are going to be talking about in this video. A battery stores chemical energy and converts the chemical energy into electrical energy. Now let's just break that down in two steps, right? So electrical energy is essentially current, and in order for current to flow, there has to be surplus of electrons in one location and there has to be scarcity of electrons in other location, right? And that is when electrons are going to flow, and this is what you would call as current. So if you take your battery, you have your cathode, you have your anode, essentially the electrodes, right? So the idea behind designing a simple cell or choosing the chemistry of a cell is fairly simple. It turns out that there is something called as a reduction potential, and electrode materials have reduction potentials. So what does reduction potential mean? So reduction potential is a property of the electrode which basically tells us how easy it is for that particular electrode to accept electrons, right? So if we take a particular material, for electrodes, say fluorine, if it has really high reduction potential, that means it's going to accept electrons very easily. Similarly, if you have a material that has a really low reduction potential, it cannot accept electrons easily. In fact, it's going to be extremely willing to give up the electrons, right? So I hope you kind of see the pattern here. If the electrode has really low reduction potential, it's going to give up the electrons. In other words, it can create potentially surplus electrons. And if your reduction potential is very high for the other electrode that you have in your battery, then that is going to be really willing to accept these excess electrons. And that is how battery packs are chosen. You take up electrodes and you make sure that one electrode can give up the electrons and the other electrode can just catch the electrons that the first electrode gives up. And this difference in reduction potential is going to determine the voltage of the battery. And that kind of makes sense because reduction potential is measured in volts. So if you subtract the reduction potentials between the cathode and anode, you're going to end up with the reduction potential of your cell. All right. So let's kind of go over a presentation where I talk about this in more detail, and let's take a look at some chemical reactions along with their reduction potentials. All right, let's get started. All right, guys. So let's first discuss the learning objectives of this session. So we need to make sure that you understand the fundamentals of batteries and you get sufficient idea on how cathode and anode for a particular battery can be chosen. And then the third objective is to understand the key performance parameters of a battery. Then the fourth point is to understand the effect of temperature on battery performance. This is also called as temperature sensitivity. The fifth objective is to help you understand the sources of heat generation in a single cell. The sixth and the final objective is to help you understand how a cooling system to basically manage the thermal performance of a battery can be designed. Alright, so battery 101s. Now these are concepts that you definitely have to remember. So make sure that you are taking notes, make sure that you are trying to memorize the concepts because it's going to be very helpful for you. Now batteries have two terminals, anode and cathode, right? Anode is the negative terminal and cathode is the positive terminal, right? Now if you take anode loses electrons easily, right? In other words, anode oxidizes easily. On the other hand, if you take cathode gains electrons easily, and essentially another way to say that is cathode reduces easily, right? So this concept is a bit confusing to a lot of people because cathode is actually gaining electrons, but we are saying that it's undergoing reduction, right? So how can something that's undergoing reduction be gaining something, right? So it kind of seems counterintuitive, but there is an easy way for you to remember this. Just remember the words oil and rig. So oil is OIL, and you can remember that it's nothing but oxidation. I stands for is, L stands for loss. So oxidation is loss of electrons, and reduction, right? Reduction is gain, RIG. So reduction is gain of electrons. So remember the words oil and rig to understand what reduction and oxidation is. So in other words, going by reduction potential, we know that cathode is going to have a very high value of reduction potential because it can accept electrons easily, and anode is going to have a really low value of reduction potential, right? And that's kind of the whole idea. And in a battery, at any given time, you have a combination of reduction and oxidation that's taking place in these two terminals. And that's why these reactions are called as redox reactions, right? Reduction and oxidation reactions. And the other thing that is very important is for automotive applications, you would prefer a battery that can be charged. And any battery that can be charged again is what you would call as a secondary battery. So choosing cathode and anode, as I mentioned before, you need to make sure that between the cathode and anode, there has to be a very good difference in reduction potential. So let's take a look at UC Davis's website, LibreText, where these values are documented. So these are off reactions, and you can see that for each and every off reaction, the reduction potential is listed. And the baseline guy is hydrogen. So the hydrogen entry in this table is what is referred to as the standard hydrogen element. You can see that its reduction potential is set to 0. I don't think its absolute value is set to 0, but for the sake of convenience, it is set to 0. It's made to 0 so that you can compare the reduction potentials of other half reactions with respect to the standard hydrogen element. And you can kind of see that lithium has the lowest reduction potential, and that's one of the reasons why lithium ion batteries are so popular. Because of the high reduction potential, you can essentially have really high voltage per cell, and that's essentially what you call as energy density. And if you have very high energy density, you can almost say that you can get more miles from your electric vehicle for a smaller battery pack weight. These two things are not directly correlated, but you need to keep in mind that this statement is not always true. Alright, so if you look at elements that are below the standard hydrogen element, you can see that the reduction potential is now positive and increases. And on the other end of the spectrum, you have fluorine, which has a very high value of reduction potential. So if you make sure that your anode is lithium and if your cathode is made up of fluorine, you will basically have maximum difference in reduction potential. Now, if cell voltage is the only criteria that you care about, then this would be the only strategy that people would use to create batteries. But as it turns out, there are other parameters as well. So if I scroll down this page, you can kind of get to see a different view. So here you can see that this is where your standard hydrogen element is. On the bottom, you basically have lithium, right? So this is kind of the ordering is opposite to the previous table, but this is a much more cleaner looking table. So you can see that positive values of potential, reduction potential, indicates that particular half reaction is going to have the tendency to accept electrons, right? Whereas lower potential means that that particular half reaction has a tendency to lose electrons. All right. So this is a very important table. Do bookmark this URL if you're interested in learning more about this topic. All right. So coming back to the PPT. Let's take a look at key performance parameters that determines how a battery pack is going to perform. Obviously, voltage is one. We already looked at it. It's the difference in reduction potentials between the electrodes. So the battery chemistry is something that typically a chemical engineer plays with. They try to come up with different strategies, different chemistries that can be supported in battery packs. And the idea is to not only optimize for voltage, but to optimize for other things such as C rate, cycle life, thermal runaway, specific energy, and cost per kilowatt hour. So we already know what voltage is. So now let's discuss C rate. So C rate is defined as current drawn divided by current drawn for 1 hour battery life. So what does this mean? So for example, let us say that you have a battery pack that has a capacity of 2 amp hour. So in other words, for 1 hour, it can provide 2 amps. So say that you have your mobile phone, right? And you are using a 2 amp hour battery to charge it. So if your mobile phone is drawing 2 amps, the battery is going to last for 1 hour, correct? If your mobile phone is drawing 1 amp, then the battery is going to last for 2 hours. In other words, the current that's being drawn, and if you multiply it with the duration, that should be equal to the battery capacity. So what is C rate? Well, C rate is nothing but the current drawn by the device divided by current drawn for 1 hour battery life. So if you take 2 amp hour, right? So what's the amount of current that you need to draw so that the battery life is 1 hour? Well, it's very simple. It's 2 amps, right? If you draw 2 amps, then the battery is going to last for 1 hour. So say that your actual device also draws 2 amps, then you get 2 by 2, which is 1, and that would be the C rate. Now if you look at the unit of C rate, that's going to be a time inverse, right? Going to be 1 by hour or 1 by second. Now what is C rate of 0.1? Well, C rate of 0.1 means you're drawing really small amount of current. You are essentially drawing 0.2 amps per hour, right? So if you're drawing 0.2 divided by 2 is 0.1, right? So C rate is very important because it affects battery lives. And a chemical engineer, when they are exploring different chemistries, they also want to make sure that the battery supports high C rates, because in specific scenarios, especially with respect to electric vehicle applications, your C rate might have to be high. For example, say that you are accelerating, right? You want more current to be drawn. Your battery's life should not be affected because momentarily the current drawn is too high. So chemical engineers are generally play with the chemistries to make sure that the C rate values supported by the batteries are high enough so that the battery life doesn't get damaged. Then you have something called as a cycle life. So cycle life basically says how many cycles of charge and discharge a battery can withstand. Now ideally for EV applications that should be a lot. So you need to kind of first define what a cycle means, right? So when we say that a battery has to go from fully charged to some percentage, right? So some percentage of usage, that percentage of usage is what you call as depth of discharge. So if you have a battery and say that 80% of the battery life is consumed before you charge it again, then that's essentially one cycle where the depth of discharge is 80%. All right. So now what would you do? You would charge the battery again and then say that you start using it again, and for the second time the battery's capacity drops by 80%. In other words, there is only 20% battery life remaining. So this is cycle number 2. So you want to make sure that the battery lasts several cycles before replacement, because if it's not going to provide the promised cycle life, a customer who is going to buy an electric vehicle from you is always going to have range anxiety, and that directly affects the sales. So any automotive companies that makes battery packs keeps a strong eye on cycle life. The next key performance parameter is thermal runaway. As I discussed before, it's essentially a chain reaction which leads to spontaneous heat generation, which increases the temperature of the battery by a really large number, right? It can go as high as 300 degrees Celsius for certain lithium ion chemistries. You can read more about that in this particular reference. The other parameter is essentially specific energy, which is energy per kg. This is again a very important parameter, and this is directly related to the difference in reduction potential between the electrodes. And I think as in any engineering application, the cost is going to be the driver. So cost can be modeled in several ways. You can look at cost per kg of battery if battery is kind of the main driver, or you can basically look at cost per kilowatt hour, and that's a common metric that is used with respect to automotive application, because you can then compare how much dollars you save by having an electric vehicle when compared to having a gasoline vehicle. All right. Now you need to understand that the above list is not comprehensive. There are more parameters that define the performance of batteries, but I would like to think that the parameters listed here are really fundamental, and oftentimes if you understand these parameters very well, you would be able to understand the comprehensive set of parameters that's listed in this particular reference. So temperature sensitivity. Now batteries are sensitive to ambient temperatures and heat generation. Now there are certain variations of lithium ion chemistry based batteries which have different temperature sensitivity limits. And if you're really interested in learning more about that, I would point you to the reference that's listed in the footer. One interesting thing that was actually pointed in that particular text was within the United States, the variation in ambient temperature across all the states resulted in a difference of battery life amongst the cars that were sold in these states, and this difference was up to 4 years, which is really crazy, right? That kind of shows how important temperature sensitivity is. In other words, so you need to make sure that while designing a battery pack, the temperature non-homogeneity is as low as possible. Thermal runaway, I think we have already talked about that a bit. So the above points essentially let us know that a battery thermal management system is essential for electric vehicle applications. Especially when you have larger battery packs, you have more cells, you need to make sure that whatever cooling strategy that you use results in a lower non-homogeneity of temperature amongst all these cells. Alright, so since temperature of the cell is kind of the key performance parameter, it's very important to understand the sources of heat generation in a battery. We already discussed this once, but this is the first time we are going to be looking at a mathematical equation. The heat generation inside a cell can be modeled as 4 parts. Joule's heating, which is because of internal resistance. Entropic heat generation because of irreversibilities in the system. Aging related effects and mixing related effects. Now, if you write down these equations in a mathematical form, you get the equation that is basically shown here. Now, this is a differential equation for heat generation. We can actually use this equation to predict how the temperature inside the battery pack is going to change. And that is what we are going to be doing in the next class. One of the things that I want to make you understand is that it is perfectly fine even if you do not understand what each of these terms do. If you get an accurate representation for these terms in terms of having the values to compute these quantities, then create a mathematical model which calculates the temperature inside a battery efficiently, right, and accurately. Now here is an important thing. That is the first requirement for you to be able to design a cooling system. You need a way to estimate the temperature distribution accurately. This can be a numerical model or it could be an experimental setup, doesn't matter. So once that is there, you can basically look at a majority of the constraints, right? So you first look at the key performance parameters of your battery, right? Once those parameters have been satisfied, then you basically look at additional design criteria. For example, what's going to be the amount of space that this battery pack is going to use? What is its weight going to be, right? Based upon this, a cooling solution can be designed. And when you use a cooling system, then there is going to be efficiency loss. And if you remember from the vehicle architecture lecture, if the ambient temperature becomes very low, for example in states like Wisconsin, you basically use power from battery to heat the batteries so that it's maintained at the correct temperature. In those situations, you end up wasting a large amount of power, right? So cooling solution has to be able to do that as efficiently as possible, right? You cannot go without heating the cabin, right? You cannot go without maintaining the batteries at the right temperature. That is a cost that we have to pay, but we have to make sure that it is done in the most efficient way possible. But then once this is done, you kind of repeat the process over and over again till you essentially get that desired cooling system. From a cost point of view, the primary thing that affects your decision is the type of cooling solution. You can go for an air-cooled solution, a liquid-cooled solution, or even end up using something like a phase change material. For automotive applications, liquid-cooled solutions are better, and there are a lot of reasons, right? So you want to make sure that your battery is first not exposed, because in case of an accident, you want to make sure that the battery is sealed as much as possible and takes as less of a damage as possible. So since the entire system is going to be sealed, air cooling is no longer an option. So the primary option is going to be liquid cooling, where you basically run liquid coolant across all the cells and make sure that everything gets cooled. All right. Now phase change materials can also be used, and sometimes phase change materials are used in conjunction with liquid cooling. All right. That being said, that brings us to the end of this lecture, and I'll see you guys in the next one. Thank you. Bye.